Okay, let's start today's session. So today I will be focusing on two main topics: longest increasing subsequence and longest common subsequence between two strings, and then I will do one interesting three-state DP question. Okay, so let's start. So longest increasing subsequence. Let's first understand what is a longest increasing subsequence. So um, if I write a number array, say 1, 2, 5, 3, 4. So the longest increasing subsequence is that we have to choose some numbers from a given array, and such that each of the numbers is greater than the previous number chosen. So if I choose the numbers say 2 and 5, then this is an increasing sequence 2 comma 5, because 5 is greater than 2. And uh, and then comes longest increasing subsequence. So among all the possible number of subsequences, so the number of subsequences is 2 to the power n. So among this all 2 to the power n subsequences, we have to choose a subsequence such that its length is maximum. For example, if we see here, if we choose say 1 2 5, this is an increasing subsequence. 2 is greater than 1, 5 is greater than 2, and its length is 3. Another subsequence, say 1 2 and say 3, this is also an increasing subsequence. 2 is greater than 1, 3 is greater than 2, and its length is also 3. But these are not the longest. So for the longest, if we choose 1 2 3 and 4, then this is an increasing subsequence and its length is 4. We can we can check that this is the longest subsequence. So this is a pretty standard DP question that you can see. So okay, first of all, I need to tell you that all the questions that have been taught in the previous session, or I will be teaching in this session, this will not directly come in your online assessments or any questions. Like, this will form a basis for you to solve other questions. These are all standard questions. Like, if you search this, you will get in GUFG. So there is no point in giving these questions to an exam. So they will frame the questions such that a part of it may be required to be solved using, say, longest increasing subsequence. Okay, so let's try to find out how we can solve it. So let's go for from an interview point of perspective. So if you go to for an interview, first they will ask you for a naive approach. They don't ask you for the most optimal approach right away, right? So what would be the naive approach? Like, uh, find all the 2 to the power n subsequences, and then check if it is an increasing subsequence. If it is, then find the length and update the answer as required. So I will not be coding that. That is very brute force kind of thing. You can do that yourself. So just I will tell you the time complexity. It would be O of n in 2 to the power n. The space complexity depends. If you are using a recursive way, using stack, then it becomes like 2 to the power n or something. Uh, or yeah, 2 to the power n. Else, I would suggest using bit masking, because that reduces the time complexity, space complexity to O of n. So bit masking was also taught in the some previous session by Onish. So now let's come to a DP approach. That is our main focus today. So 2, 7, 4. Yeah. So now let's think about how then this DP work. So the longest increasing subsequence is that if I choose any element, say AI, then all the elements chosen before it, aj, such that j less than I, these ages should be less than a of I, right? So there can, by the definition, increasing subsequence, a of j cannot be greater than a of I. So, and another thing, there are two forms like longest increasing subsequence and longest strictly increasing subsequence. So strictly increasing means a of I greater than a of j for all j less than I, and only increasing longest increasing subsequence is a uh, a of I greater than equals to a of j for some j less than I. So we are just focusing on this one. This is pretty similar, like just one uh, different comparator. So coming back to here, by definition, a of j will be less than a of I. So uh, we can check. So let's again focus on the primary points of dp. So when we are at some state, say a of I, we can assume that all the previous states are already calculated. So we have, say, so what are the dp states that we will be thinking here? So what are the dp states that we can have? So here we will be focusing, so dp of I would be the longest increasing subsequence where the last element, I repeat, the last element is a of I. Okay, so again I'm repeating. So dp of I is the longest increasing subsequence up of the subarray 0 to I, such that the last element is a of I. Okay, so let's try solving for this one. So first of all, the first element, it is itself an element. So if it is an single element, then it's all obviously an increasing element. So that is always valid. So dp of 0 would be 1. So now dp of 1. So how we will go on with that here? So we have to find all these elements, all the elements that are before it, which are less than this element. So there is only one element here, and this is less than 3. So how we are doing here? So dp of I would be max of, so here I'm writing the transition equation. Max dp of j. What is dp? What is here? Uh, dp of j such that a of j is less than a of I and j is less than I plus 1, 1. So this is the transition equation. Let me explain it. Okay. So as I explained, I have to find all those elements which before a of I, which are less than a of I. That's then only we can make that increasing subsequence end with a of I. So we have found that, and we have to find max of the dp of that. So among all those elements, we have to find that one, that element where the longest increasing subsequence is maximum. Like uh, we have to find, so here in this example, only one element is here which is less than that. So one is less than that, so this qualifies as this one. And here its dp of j value is 1. So max of this value becomes 1 plus 1. This plus 1 is that I am increasing, appending one another element a of I to some already existing subsequence. So this becomes plus 1. So now dp of this one becomes 2. um, just one, who called? One minute, please. Okay, sorry. Yeah. So where was I? Yeah. So this one becomes dp of this becomes 2. So I you can see here 2 means the longest increasing subsequence ending at this position, the length is 2. So you can see it is 1 and 3. So it is 2. So the transition states is clearly given. So let's make a code over here. So for I equals to 0, I less than n, I plus plus, for j equals another thing. Let's say I'm storing this max value in an array variable, say m, which is initially 0. So for j equals to 0, j less than I, j plus plus. Now here comes, like, if we have to check whether this element a of j is less than a of I or not. So if a of j is less than a of I, m equals to uh, max m comma dp of j. So we have got this m here. So now we will update dp of I. dp of I is equals to m plus 1. This is a pretty standard dp question. So pretty standard complexity as well. This is O of n square space time complexity, and space complexity is equals to O of n, right? But this is not a very good approach. Even if it's dp, we can do better, right? So now we will think of a better approach. Let's try doing it in a better. So now let's find a different approach. So this approach is also very useful. First of all, it has a better time complexity. On also, if you see the previous approach, there is no direct way to actually get the longest increasing subsequence. So if you are asked to print the longest increasing subsequence, it will be difficult. You have to backtrack from dp of j and stuff. So let's see another approach. So now let's create that longest increasing subsequence as we go from this side to this side. So let's um, first understand the idea, then we will go on to the example. So for any who is calling? Uh, so uh, so if we create, let's first understand. So if we create a longest increasing subsequence, in order to add more and more elements, the intuition is that for at any position we will try to keep the smallest element, right? So give an example. So there is say the longest increasing subsequence at some point, say 1, 3, 5. So now the next element say a 2 comes up. So where so we can try to put 2 at some position which such that it maintains this list, this longest increasing subsequence, but at some point it reduces its value, value of the element, not the length. Right? Let's see if we put say 2 at that position, then it becomes 2 to 5. It is also valid, but let's see some other options. We cannot put 2 at this position, obviously, then it does not remain a longest increasing subsequence. So if we put 2 at this position, it becomes 1, 2, and 5. This is always beneficial. Why? Let me give you an example. So now let's say another um, element comes up. Let's say a 3 comes up. So let's say a 4. Yeah. So another element comes up. Let's say a 3 comes up. So if this element would have been the same, uh, then there was no point in adding those. Like uh, if we now again we will be doing here, we will be adding the first element which is greater. So if we put it here, so this becomes 1, 2, and 3. And now let's say another element comes up, say 4. So now if there are 3 points, like we have added a 2, we have added say a 3. So now this 4, if this sequence was all, like we haven't changed this one, 1, 4, and 5, then uh, adding or removing this 4 would have made no sense. Like if we had added like 4 in place of this 5, then the length remained say 3 only. But now that we have added a 3 over here, the sequence is now 1, 2, and 3, and now we can add the 4 over here. So 1, 2, 3, 4, the length is now 4. So this is all obviously beneficial. So the idea over here is that we keep we keep the longest increasing subsequence as we go, and then at any point we find the smallest element. I repeat, the smallest element that is larger than a of I, and replace it with a of I. And the other case is that if it is larger than the largest element already present in the list, we add it to the end and increase the length by 1. So how we will code that? For I equals to 0, let's say the longest increasing subsequence, say a list. For I equals to 0, I less than I plus plus. Now here, instead of searching for the entire thing and stuff, the idea here is the longest increasing subsequence is an increasing subsequence. So why do we need to go for a linear search? We can easily do a binary search. So let us assume there is a function, a binary search, which finds the smallest element which is larger than that element. So index is equal to binary search of say lis comma a of I. So here we find the index. If um, a of I is greater than lis of uh, -1. So okay, this is like for the Python syntax. So -1 means the last index. Okay. For C++, you can just length of lis -1. This is just it. So if this is that, like it is all larger than the largest element already present in the list. So we will just add it. Lis dot append a of I, else we will replace this some element with this element which we have already got from ind. So lis of ind equals to a of I, and at the end we will return length of uh, lis. So this is a much better approach. We are getting the longest increasing subsequence as well as reducing the time complexity. So the time complexity is O of n into binary search. For the binary search, we have log n, so n log n. Space complexity remains O of n, but we are getting actually the uh, longest increasing subsequence, actual longest increasing subsequence in a much easier way. Okay, so let's do one quick example. So I have a sequence at 2, 5, 3, 7, 11, 8, 10, 13, and 16. So I want you guys to just take a pen and paper, write down this array and try to solve it with me. Okay. So first element, obviously the base. So approach one. So let's try it in of n square. First element, obviously it is the separate case. We can always make um, one the first element as its separate lis. Just a moment. Hello. Hello. Ah, yeah. Sorry. Shayok, can you please again repeat the approach once? Which approach you are talking? The n log n one. Hello. Yeah. Okay. So I will just explain it once again. So here, as we are moving, we are keeping in hand the longest increasing subsequence that we have got. So from this example here, so 2 is not needed. So just remove it. So let's say the sequence is 1, 2, and 5. So a 3 comes up, right? So if we, let's say we change it from this 5 to 3. So now the sequence becomes 1, 2, and 3. So now after that 3 or 4 comes up. If this sequence had been 1, 2, and 5, then we cannot add a 4 to the end. We can obviously add 4 over here in place of the 5, but that doesn't increase the length of the subsequence. So if we have added changed 5 to 3, then we can add a 4 to the end, and the length of the lis becomes 4 in this case. Okay, so that's how this approach works, and you can check it using different cases. that adding this any element to the smallest element that is larger than it is obviously the best. Like uh, we cannot add it to some greater element because then it will not remain along LIS. Like if we had gotten say a 1 instead of a 3, we cannot put 1 in place of this 5, then it will not be a, then it would
Like,
not be. Hello.
so if it was say 135 and 2 comes, so we will add 2
Yeah,
in place
135.
of 3. 135
The
and 2
original sequence was
comes.
1, 3, and 5.
Yes. So, and if 2 comes, so we are adding 2 in place of 3. Or,
Yeah, exactly. So if it was 1, 3, 5, and a 2 comes, we will place it over here. Okay.
okay, so we are finding like if the element is smaller than the element to be inserted, we are replacing the element which is larger than that.
The smallest element
And
that is larger than that.
yes, and if the element is larger than, we are inserting at the last, like
Yes,
1 2
then
3.
it is increasing the length by 1.
Okay.
Got it?
Yeah.
So let's just do one example that will clear up. So for 2, this is obviously 1. For 5, we will check all the elements previous than that, which is greater than that, less than that. So 2 is less than that, so 1, and then plus 1. Remember the recursion relation, max of dp of j plus 1, so it's 2, 3, 5 not less than that, 2 less than that, so 1 plus 1, that is 2. 7, all of these are less than that, so we have to find the maximum of that, so it's any one of among this one, so it's 3. 11, all of them less than that, maximum of that, so it's 3, this one plus 1, 4. 8, 2 less than that, yes. 1, 5 less than that, yes. 3, yes. 7, yes. 11, no. So maximum here is 3, so it's 3 plus 1, it is 4. 10, 2 yes. 5 yes. 3 yes. 7 yes. 11 no. 8 yes, so it's 4, maximum is 4, plus 1, it's 5. 13, 2 years, 5 years, 3 years, 7 years, 11 years, 8 years, 10 years. So all of them are less than that, but maximum is 5. So it's 5 plus 1, it's 6. And just a minute, 2, 3, 7, 1, 2, 4. So
Okay.
16, all of them are less than that, but maximum is 6, so it's 7. So the maximum is 7. So let's now do it using the second approach, n log n. First, uh, it is an empty, so we can just directly put the 2 over here. Then comes a 5. 5. So this is the LIS sequence. Okay. So 2, 5, we can put it there. Then comes a 3. So where should we put it? We should put it the smallest element, which is larger than that. So in place of this 5, we place the 3. 7 larger than that, place it. 11 larger than 7, place it. Now 8, the smallest element larger than that, this is 11, so place an 8 over here. 10 larger than that, place it. 13 larger than 10, place it. 16 larger than that, place it. So we got the largest increasing subsequence itself, the length becomes 7. And here we did not get the LIS, but here we are getting the LIS, so this is better obviously for n log n. Okay, so got it. So now so here we complete the loudest increasing subsequence. Let's move quickly to the next approach. Okay, first Is there any question? Anyone who did not understand, you can speak up. So let's get to the longest common subsequence. What is the longest common subsequence again? So let's say there are two uh, a- so there are two strings s1 and s2. The longest common subsequence is such a subsequence which is common to both, but it is the largest. So let's search for the common subsequences first in this example. So it is a, it's common. There is b, uh, one length is over, so two length ab, yeah, ad, no, bd, no, abd, no. So the largest one is ab, which is length is 2. So how are we going to solve this problem? So let's come up with some intuition. Obviously, we are doing a session on DP, so it will be solved using DP. So previously we had a one-state DP question. So this one is a two-state DP question. Here we will try matching each of the elements of S1 to all the other elements of S2. So let's say we are matching this C and D. And from the definition of DP, we will assume that all the previous states are calculated. So C and D, this doesn't match, right? So this two cannot be a part of the LCS because these two are definitely not matching. So instead of matching these two, we will match either this C with some element preceding this D, or we will match this D with some element preceding this C. We can have some D over here, then that will match and that can become a part of the LCS. That is the idea over here. Instead, if this matches, say let's say this one, this B and this B, these two are matching. So if these two are matching at this point, one thing is that assuredly, if instead of matching this B with this B, if we match this B with some B preceding this B, let's say there is a B over here. If we match this one, we can guarantee that the length of the longest common subsequence will be less. Why? Less or equal? Because let's say some B is before this A. Okay, so if we match this becomes BABD and say ACB. So instead of matching this B with this B, if I match this B with this B, then previously there is one matching element, right? A. So if we have matched this B with this B, then the LCS will become AB. But if we are matching this B with this B, there is no element previous to that, and obviously non-matching. So the LCS becomes B, which is obviously less. So this proves that it is always beneficial if two elements are matching. We will match those, and we take some already calculated LCS from previous to this one, previous the matching elements. So it is a pretty straightforward DP question, and let's try solving that. So for um, I equals to 0, acha, uh, for I equals to 0, ah, let's code this one. For I equals to 0, I less than n, I প্লাস ওয়াস ওটা সরি তারটা সরি তারটা সরি so n is length of one string and m is say length of the another string. So for j equals to 0, j less than m, j plus plus. So um, there are two conditions: either this a plus s1 of I will match with s2 of j, or it will not match. So from our discussion, if s1 of I matches S2 of J, then we will obviously keep this in the LCS, and we will we will ask for some LCS that is made using uh, this part and this part. Okay, so this B and B is matching. So we from this discussion A and A is matching. So we will ask for some LCS over here. So how can we get that? So let's understand the DP steps. So DP of um, I and J, the two-state DP, I have said, the DP of I and J is the LCS such that LCS among the substrings S1 0 to I and S2 0 to J. So here we are matching S1 of I and S2 of J. So we need the LCS among the previous elements. So what is that? It is dp of I minus 1, j minus 1. So keeping aside the ith element of S1 and jth element of S2, the LCS is dp of I minus 1, j minus 1. That is the maximum according to our construction. So dp of I j equals to this one plus 1, because this is we are matching this, and hence the LCS is increasing, the length is increasing by 1, so it is plus 1. Else now it is not matching, right? So from our discussion we will try to match B with some element preceding this. So what is that? That is dp of I up. So matching that means what? LCS of S1 0 to I and S2 of 0 to j minus 1. So dp of I j minus 1, matching this I to some element among this j minus 1, or we can match this element S2 to some element preceding that. So that is keeping j one element before still I minus 1. So it is dp of I minus 1 j. And obviously what we do is we need the largest longest um, longest common subsequence. So dp of I j equals to max of this two. Pretty straightforward question. uh, the complexity is, there are two loops, so it is O of n m. Space complexity are two-state dp, the dp table itself, so it is O of n m. At the end we at the end we would return dp of n minus 1 n minus 1. Okay, got it? Any question on this question, on this topic? No, right? Okay, so let's come up with a question, right? Possible this one. Let's try solving this one. A B C D G H and A E D F H B. These are the two strings. The constructing the table, a 6x6 table. Let's try solving it. A and A matching 1. B and A not matching. Either the previous one dp of I minus 1 j or dp of I j minus 1. There is no I minus 1 j, so we can assume it to be 0. So this one, max of those two. Ca not matching previous one, da not matching, g not matching, ea not matching. So max of this one or this one. This one, let's assume 0. So this one, be not matching, ce not matching. Max of this one or this one, both are same. de not matching, ge not matching, he not matching, da not matching. Max of this one and this one, 0 and 1, 1. bd not matching. Max of 1 and 1, 1. cd not matching. Now dd matching. So from this equation, when it is matching, dp of ij equals to dp of I minus 1 j minus 1 plus 1. So dp of I minus 1 j minus is 1 plus 1, that is 2. gd not matching, max of this and this, 2. hd not matching, max of this, 2 and 1, 2. fa not matching, max not matching, not matching, not matching, max of 2 and 1, 2. Hello, 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 hello.
Yeah, yeah, yeah. Audible.
Please call it. F and G not matching, max of 2 and 2, 2. FH not matching, 2. HA not matching, max 2. Yeah. So H and H is matching. So this one plus 1, 2 plus 1, 3. BA not matching, 1. B matching, 1 plus 1, 2. BC not matching, max of this and this, 2. BD not matching, 2. BG not matching, BH not matching. So it is this one. So it is 3. And you can also check that it is A D H, A D H. So that is the longest common subsequence. Okay, got it. Any questions? Let's move on to the three-state DP question. Um, Actually, I will give you the time to solve this one. This I will. Anyone, Kiran or someone there in the chat? No. Okay, so I'm giving you this question. Given an n cross m matrix, so an n cross m matrix is there, right? And all the adjacent movements, so this says adjacent cells are this one, this one, this one, and this one. All these movements, profits are given. So when you move from one cell to its adjacent cell, you get some money. Okay, let's say you can start from any cell and you can move to all the 4 directions, and you can use the same path twice. Like if you go from here, go from there, there, and again you can go to there. So, and the number of steps is given as k. So you need to find the maximum profit that you can achieve if you try moving, if you move k steps. The conditions are simple: starting from any position, movement through each door. Let's say doors. This adjacent, each of these say a door. So you can move through the same door any number of times and bidirectionally. What is the maximum profit that you can get? One of the hints is it is a three-state dp. And just write down this question. I will also post it in the Discord. This will be an assignment to you, and in the later doubt clearing session, or in the next session, I will just help you to this problem. This is a very good problem. I took the inspiration from one code forces contest. So uh, I will just copy this. I am putting it in the chat. So okay, got it. If else is being used, increase the value of one. If letters are the is to increase the value by one. If letters are same, you increase. Viva, I don't understand. If else is being used to increase the value by one, if letters are the same, we increase. Can you just explain a bit more? I don't understand what you're saying. Okay, so what is this? Can't we keep moving through one door back and forth k minus 2 times? Yes, you can. Uh, yes, you can do that. But I don't think whether it would be profitable or not. Okay, I will give you an example, right? Like there are say three. Let's say I'm just talking about the doors. Okay, not the these are not the cells. These are the doors. Okay, so first door say profit is 9, second door profit is 1, third door's profit is 8. So if you keep moving back and forth this 9 and 1, it will give you some profit. But if you go from this to this, then it will give you much more profit. So it is not beneficial to move to the same door back multiple came by 2 times. Okay. So I posted it in the chat box. So this will be your assignment. I will also post it in the Discord. Try solving it. It's a very good question, a three-state DB question. Very, you know, purely DP question. You don't have to think about any other things. Okay. So I think we will end the session today. Is there any more questions relating to any of the topics or this particular question that I gave you? No, right? Okay. So see you. Let's end the session over here.